Hey everyone, how's it going? Welcome to the stream. Let's give me a second. I'm gonna mute my phone over here. All right. Okay, so let's get right in. So those of you who are watching me a couple nights ago, you know that I was struggling to try and track down a call stack tracking bug in my debugger. Specifically when playing the game Bedlam. At the end of the stream, as I was reflecting upon how to perhaps figure this out, I actually came up with this idea that perhaps the best way would be to try and detect when the stack pointer is being changed and being basically becoming greater than effectively becoming greater than the stack pointer as it was when a call stack frame was created. So just to sort of repeat very quickly, hey Jono, how's it going? Long time no see live. So I'll just repeat quickly the way I implemented call stack tracking. So what I did is whenever an instruction is executed, I call this function here, post-op update call stack. And the core of the logic is to grab the program counter and to say if the instruction that we just executed is a call instruction, and call has a very specific meaning here. By call I mean any one of these. If it's a branch or a jump subroutine, so branch subroutine, jump subroutine is also software interrupt. So if it's any one of those, then we just made a call. If we just made a call, then we need to get the return address of that call. And we do this by inspecting the stack. So if we go back to this function, for any one of the normal branch subroutines, what happens is these instructions first push the return address onto the stack and then they jump. So if, you can see here that all I do is, so at this moment S, which is the stack pointer, points to the current location on the stack where we just pushed the program counter, so I simply read it back. Similarly for software interrupts, we push all the registers on the stack, and so the PC happens to be at offset 10. Yeah, I've been good, thanks. And you? So the whole idea is, okay, we detected a call, so get the return address and then push a stack frame onto my call stack, and we record a bit of information here. We record the basically the pre-op program counter, so the address that we were at. So this is like the callee address, actually. I think we look here. Yeah, that's the callee address. So where we were called, this function is called from. We also store what I call the frame address, which is a little bit unnecessary, but it's where we are at that's like the address of the start of the function. And I also store the return address. So that's the thing that we just returned here. And then I recently added the stack pointer. But this stack pointer here, I didn't have it originally. Because what happens is that then, more instructions are called, and then eventually, we'll have like a return function, return subroutine, RTS, let's say. So let's say we did a JSR, a jump subroutine. Eventually we'll do an RTS, return from subroutine. So the way we detect that is I'll say, well, if at the top of the call stack, if the last return address is equal to cur op PC, so if the current program counter, the current address, is equal to that return address that we pushed on the top of the stack. So if we go here, I'm just really comparing it to that return address here. That means that we've just returned, right? And in that case, I basically pop I pop the call stack. This is all like debugging stuff here that I don't need anymore. Just remove all this stuff here. all of it's actually going to be deleted very shortly. Okay. So, all right. So the thing is, this is great and works most of the time. It works as long as the program behaves, properly. Like if it makes calls, it always returns, right? Now, of course, should be the case for anything that we write in C or C++ and that we compile, because the compiler will produce this sort of canonical jump return type of code. I suppose there might be a way in C or C++ using gotos to get it to do the wrong thing, although I haven't ever tried to go to outside of a function scope, so that may not even be possible. But anyway, the thing is that I'm not dealing with regular programs in general. In fact, all of the games that were written for the Vectrex at the time were written in assembly. And Bedlam is a good example of a game that does lots of weird things. And one of those weird things is what we're going to see today. Because what I thought about last time is, like, rather than just looking for when have we hit the last return address, I was like, why don't I instead look at, remember this, like save off the stack pointer when we push a frame, and then continuously look to see is the current stack pointer ever greater than or equal to, actually, to the top frame stack pointer. So if you think about it, like every time we make calls, we are pushing, the program counter, the return address, onto the stack. And what that does is it actually makes the stack pointer go down, like it decreases, okay? So, you can think of it as we have finished our call when the stack pointer has returned back to the point it was at just before we made the call, right? And in fact, the more I thought about it, the more I realized that's probably the best way to do call stack tracking, and we'll get into that. But for now, what I did is I added this else branch, and I said here, make sure that S is still greater than the top of the stack, of the top of the stack's S. Normally, when we call a function, BSR, it eventually returns, say via JSR or via pull SPC. There are different ways you can return, right? This is just as valid here. You just say, I'm going to pull from the stack the value and put it into PC. So it eventually returns by setting PC to the address of the instruction following the call instruction. Now, okay, I didn't write any more here, but basically what I'm doing is I'm saying every instruction, grab the top of the stack, so the last thing we pushed onto the stack, and grab its stack pointer. Now, if that value, this is greater than 0, this is just sort of a bit of a hack because I have this initial push that I do up here where I push, it doesn't really matter. So when it's a valid top of the stack, and then what I look for is the current stack pointer greater than or equal to this top stack? Because if it is, that means that we just returned somehow without going through this code here. So this is like the, what the hell, right? So this is how I detected the problem in Bedlam, and I'm going to show you guys that right now. So let's just hit F5 here. Excuse me. All right, so here we are. I have a breakpoint here. I'm just going to delete my breakpoint and just continue. And remember, this bug happens after we die and are spawned again. Oh, and there we go. In fact, I guess it happens upon death. So here we are, and we've hit this, right? And like, if we look carefully, you know, if I change into hex here, just for a second. So currently the tops of the stack in our, like the top frame in our call stack says that the stack was at CBEA when we pushed this top frame. But right now, if we look at the CPU's registers, so let's do that here in my debugger. So there's S. So CBEA, right? So it matches. This means that we somehow returned, the stack returned to where it was when we pushed the PC, but we did not detect it as a return. So something weird happened, right? So now at this moment, what I do is I tell my debugger, can you please break into the debugger? Hit F5, and we go into our debugger here. And we take a look at the trace. We'll look at the last 100 instructions to get a feel for what just happened. You can ignore this last line because remember, this is going to be the line of the current instruction. I actually think that what I'm going to do is I'm going to make it so that trace has sort of a border, like trace start, trace end, because it's a little bit difficult now that I also display the current line. So it can get a bit confusing. Like over here is the line where I ask for the trace, and then when you read the trace, you might think that this line here is part of it, but it's not. The trace actually starts here. So that's something I need to do. But in any case, if we look here, this is the instruction that caused the, you know, the problem. This instruction is a pull stack into X. So what it's actually doing is it's pulling the program counter that was pushed onto the stack previously, and it's not pulling it back into the program counter, because if it had, then I would totally have detected it right here. My current program counter would have contained the last return address at the top of the stack, and that would have been normal. But here it's pulling it and putting it into X. Now, that's weird, right? And in fact, if we just step a little bit more, oh yeah, now I need to disable this because it's going to be true over and over and over again. So if I just step a little bit more, I want to just show you something. Okay, so after we pull that stack, we do some decrement here to some value in memory, and then we branch if less than or equal to some offset. And then here's the interesting bit. We jump to 00FD, and then we call CWAI. So this here is 00FD. If we look at the backtrace, it is, let me see if we can see it. Well, here it's 00FF. But basically 00FD is sort of like the beginning of, like, it's kind of like the start of the initial address of the function that kind of starts the game, the round, if you will, okay? But what they've done here is rather than do a normal return, they're like, oh, we just died, we know where we are right now, so let's just pull off the PC, the program counter, just, thanks for the follow, Fufugut, appreciate it. Yeah, so what I was saying was that what the game is doing is it's saying, okay, you know, we know we're done, we know where we are. Rather than return, let me just pull that thing off the stack because you know, we're not going to be doing a normal return. So I'm just going to pull it, throw it away because X is not used, and then I'm just going to jump straight into the beginning of this function, and we start all over again. Okay. If we dig just a little bit deeper, if we go up a little bit higher, we should see a call somewhere. I saw this earlier today. Where is it? Where is it? I think it's up here. Here we go. Jump subroutine. Okay. So this line right here, this is the jump into the subroutine that we never returned from. Okay, and you can see this because you see when we jump there, the first address of the subroutine is 0796. And if you look at my backtrace, right, there's 0796. That's like the address of the function that we're in. This is the one that I'm not correctly popping off. you know, because I'm not returning from it correctly. So here we are, we jump into it, and then we come all the way down. And just to show you, if you think about it, before we jumped into this to this function, we were at 0229 in memory. So normally, the return address should be the address of the next instruction after 0229, right? Like you call this, and when you return, you want to return not to this instruction, but to the one that follows it, okay? That's how it works, right? So what would be the address of the following instruction? So I believe that this is a 2-byte. Yeah, you can see here it's a 2-byte instruction. Therefore, it should be 29. What is it again? It's not 2A 2B, is it? I always forget. I'm actually going to see it over here. Sorry, just yeah, exactly. So after 29 in hex, it's 2A and then 2B. So 022B should be what the program counter should contain as a return address. Okay, so that gets pushed onto the stack, and then when we pull it into X, you can actually see here in my debugging stuff that X over here, I'm just going to highlight the line, X actually contains 022B, right? That would be the return address. Normally, if this had been a pull S PC, that would have gone into the program counter and I would have detected it as a proper return and everything would have been fine. But this is why it's not working, because Bedlam is doing something wonky. Okay, so this is the answer right here as to why my call stack tracking is inconsistent or broken in Bedlam. And you know, just to show you like why this is a problem, right? So if we just continue, right, and here I'll just like let myself die a few times here. Okay, if I stop right now and I do a backtrace, so already you can see that in my backtrace I have twice 0796, right? I think if we continue going, we end here. Let's do one more time. Okay, let's backtrace again. So now check out my call stack. Right? Look at that 0796. There's like 5 times 0796 here. Because I'm never detecting the fact that we're returning this way, and so they just kind of remain on the call stack, which is basically garbage. Okay. So now we know what the problem is. How do we fix it, right? Okay, so I wrote down some notes thinking about it today. So I'll just kind of read through it. So as I said, my current method is to track when PC becomes the return address. But this fails in cases where the code does weird stuff, like in Bedlam, which pops the return address off the stack without setting PC to it and does a direct jump to the start of a function. To do, change call stack tracking to track when S is greater than or equal to the top S. So that's in fact what I'm doing here to detect the problem, but rather than do it just to detect the problem, let's do it as the de facto way, potentially. In fact, I actually wrote here, if you consider programs doing really weird stuff, like a program could be like, let's say there's a game, like Bedlam only does it at one level, but you could imagine any game written in assembly doing something like, it knows it's 3 levels deep, 3 functions deep, and therefore on the stack there's like 3 return addresses. And maybe it decides, you know what, I'm just gonna pop off those 3 into X, ignore that, and then jump, right? That might happen. So I can't even make the assumption that that's going to happen exactly once. Although I do think, no, that's it. In fact, one instruction can pull multiple values off the call stack. That pull S instruction, if we go take a look at it in the CPU, I was just thinking, can it really happen in one instruction? I think it can. If we look up pull S here, so pull from the stack. And just wait for IntelliSense to wake up here. Okay, so here, what can it do? Let's see. So depending on which bits you've set up, it will, maybe actually it only pulls one value. I thought you could, oh no, that's it. Sorry, I'm being dumb here. Yeah, so you can actually pull 1, 2, 3, 4, 5, 6, 7, I guess 8 values off the stack. And basically the way it works is you specify into which target register. So depending on which register, it'll either pop 1 byte or it'll pop 2 bytes. You know, so in this case we did a pull S X. So we pulled from the stack into X, so it actually popped you know, the first 16 bits or 2 bytes into X. But if we put X comma Y comma whatever, okay, well that's the PC one. So let's say X comma Y. In fact, we could say A, B, X, and Y, right? That would end up pulling off, you know, here 2 bytes plus another 2 bytes plus another 2 bytes, right? So that's in one instruction. We could actually remove 3 program counters off the call stack right there. So back to what I was saying, I can't even assume that it's just in one instruction, so I have to iterate over my stack frames from top until S is less than the top S. So back to the state where the current top frame, its stack pointer is not, you know, larger than or equal to that of the current stack pointer. So in case multiple red addresses are popped at once. So I'll just put an example here. Pull S, A, B, X, Y. Let's just say. One issue I will have with this is next and finish. Yeah, so I was thinking about how I implemented next and finish. These currently work by setting once breakpoints. So I call these once breakpoints. These are breakpoints where you set the breakpoint and then once the breakpoint trips, it removes the breakpoint. So I don't know what else to call those, but I call them once breakpoints because they'll trigger exactly once and then they'll be gone. Sort of ephemeral breakpoints. So I showed this last time, but you think about like the next, right? I'm about to step. I'm at a jump subroutine instruction. I don't want to go into it. I want to just step over it. So that's the next command. So what I do is I just say, okay, what is the address of the next instruction after my current one? Set a once breakpoint on that, and then just continue. And it'll just run, and then when it hits that breakpoint, it'll stop. So then I will have effectively stepped over that subroutine, okay? Finish is sort of similar. In finish, I look at the call stack and say, well, what's the return address? And I'll set a once breakpoint on that, and then I'll just continue. And as soon as I hit that breakpoint, we are now out of the current function. So that's a step out. The thing is, as I wrote here, but if we hit the weird case, like what happened with Bedlam, we won't stop correctly. What it means is that we'll have these once breakpoints still in my breakpoint list because I'll never have hit those addresses, right? Also, my current method of setting once breakpoints doesn't do the right thing for recursive calls, though maybe that's expected. So yeah, so when I was thinking about that is like, right, let's say I want to do a next over my current function, but that function calls itself or calls another function that calls itself. Then when I hit my once breakpoint, I actually won't be at the same level in the stack. You know what I mean? So that's the kind of thing that can go wrong with my once breakpoint technique. It's simple, but maybe too simple. So maybe what we need to do is just delete these breakpoints and warn the user. This is an exceptional case. So does it make sense to actually break when something weird like this occurs, especially if we get multiple pops? That could be weird. See, I was thinking about the case of like, this here. When this happens, I can detect it, and I can detect that I have these breakpoints that may have been set. Maybe I should just delete those breakpoints and just warn the user saying, hey, something weird happened. We're not returning normally, and we're never going to hit these breakpoints. So, just letting you know. Which kind of sucks, but so that's one thing. Next, so now I was thinking about these two and how I would implement them differently. So let's say we're about to execute an instruction. We know the call stack size will increase by 1. So, right, because if we're about to do a next instruction on top of an instruction that is a call, like a jump subroutine. That implies that normally we're going to step into it and the call stack will increase by 1. So we want to break when it drops back to the current size. So just before it gets incremented. So let's say we're somewhere in our code, we're about to execute a jump, the call stack size is 3, right? So if we jump, it's going to push a call stack frame and the size will go to 4. So what we can think about is, well, we want to break as soon as it goes back to being 3. It's 4. Maybe it'll become 5. It'll become 6 because we'll keep jumping. But eventually it'll come back to 5, come back to 4, come back to 3. At the moment it becomes 3, it means we just popped a call stack frame and we're done. And that's next right there. So that's a different way to implement next. If we somehow drop to less than the current size, that means our breakpoint became invalid. So that's to detect the case that we're talking about, like, this here, popping multiple things. So we could detect that. So we don't break and just warn the user and delete the breakpoint. So let's just go with that. Finish, we can do the same kind of thing. Also in terms of the size of the call stack. So if you think about finish, we're executing, let's say we're, call stack is 3 frames deep. So we're like, we called. We're executing some code and then we type finish. We want to come out. So what we can do is we can say break when the call stack size will be whatever the current size is, so 3 minus 1 exactly. So I know that when I finish my function, it'll be when the call stack size goes from 3 to 2, right? So like for next, if it's less than, just like for next, if it's less than the current size minus 1, in the case of the exceptional thing, we don't break and we warn the user. So if the weird thing happens, we can detect that. So basically it's the same mechanism for both. It's just which call stack size are we tracking, right? So that's the plan. That is my plan right now. And that's what I'm going to try and implement now. I'm super thirsty. I've been sort of under the weather, so just getting really, really thirsty. Okay, so why don't we get into this? So first thing I'm going to do is I'm just going to start removing all this debug stuff. I'm going to leave this here because I think this should go back to being an assertion. Maybe not. Yeah. Yes, it should go back to being an assertion. Because once I fix all this, then we should never be able to have the case where the pre-op PC, so the program counter, is equal to the last callee address, because that means we haven't popped, because that's how all of this started. So I'll just leave that here. This should go to do re-enable this assert. I can't do it just yet, but I will do it. Apart from that, there's a whole bunch of other debug stuff I got to remove. Let me just take a look at what I did here. Yes. All this stuff about instruction count. Yeah, let me get rid of that. In fact, you know what I'm going to do? it's going to help me if I just reset to here in mixed mode, because then I can just go over my diffs and then revert that way. So here's the diff. So I don't need this anymore. I don't need this. Though, do I want to keep this just for... Okay, yeah, you know what? I'm going to keep it just a little bit longer. These are some actual bug fixes. Yeah, I'm going to keep this just a bit longer because it was useful to be able to look at the call stacks. I will delete it afterwards. Okay, pushing, that's fine. Yeah, this is all good. Right, so this I don't need anymore. And I don't need the instruction count. All this debug stuff. Okay, that's my print stuff. I'm just going to keep that there for now. Let me see. Make sure this still builds. And I'll go look at anything else. No, that's fine. Yeah, okay. All right, everything's building. Okay, so okay, breakpoint. Where's my, oh yeah, I can't use that. B breakpoints. There we go. So right now I have these instruction read, write, and then I have this thing about once. So this is not going to help me. So I'm going to need to have something special here to be able to detect when we've hit the current. If I'm going to be looking at the call stack count, I'm going to need to like beef up my breakpoints. In effect, I'm going to need some kind of conditional breakpoint. But not a condition written by the user, but a condition written by me in my debugger. Does the stack on the Vectrex CPU overflow? If Bedlam kept going past the allocated memory, I assume it will wrap. Yes, definitely. It can definitely overflow. So the thing is that the stack pointer itself, right? If we go look at the CPU here, so where is S here? So the stack itself is you know, it's a register that holds an address. I'm not finding it, but here, hardware stack pointer, right? So it holds an address. So the thing is that, you know, every time you push, it just decrements this value or writes at the, or decrements and then writes, decrements and then writes, you know. So if we look here at like stack, I don't remember what I called my function, push, oh no, sorry, it's in CPU here. So like here, if we push, let's say 1 byte, right, we write, we decrement the stack pointer and then we write the value there. So since it's just an address, eventually you can just keep writing, and you'll, you know, you'll start writing over data. So it won't overflow in the sense of wrap, right? But it'll overflow, like it'll basically start writing over user data. It's kind of, you have to kind of manage your stack yourself, right? The memory map here kind of gives a clue about it. So let's see here. Where is it again? Ah, here we go. So see here, it says, this is the area, the 874 bytes. It's a very tiny area from C880 to CBEA can be used by the programmer, and it includes the system stack. So C880 is like the initial address for your data, and CBEA is the initial address for the stack. Right? So if we go look at PC here, I think we have a place in reset. Reset here. Stack. So BIOS. So the BIOS actually sets it. It's not the CPU, but it sets it to CBEA, which is the very last address. So the stack basically, I'll show you here. This is a stack, and this is the program. Like this is where your user data, like your variables, can be stored. You know, your global variables or whatever. And as you push to the stack, this gets closer and closer. And as you write data to the variables, this gets, goes like this. So normally what you do in a program is, you'll have decided up front how many global variables you'll be using maximally. And so let's say you decided, I don't know, I need 20 bytes of variables, right? So, so that's 874 minus 20. So that leaves you with 854 bytes for your stack. Maybe 20 bytes is too little there. I'm sure games use a bit more than that, but probably not much more. And one thing I noticed in Bedlam, and it's probably fairly common, is that they sort of split the stack and said, we'll have, let's say, 128 bytes for normal stack stuff. And when there's an interrupt, they actually they save the current stack pointer, they move the stack pointer even closer, and they'll say, like, now we have this other range for the interrupt service routine, like the interrupt call, to have its own stack space. And then it'll kind of restore back to where it was when the interrupt is finished. So yeah, it's a lot of very careful management. So yeah, let me think here what I'm going to do with my breakpoints. Back to my debugger here. There's a place where I do check for breakpoints. So right now what I do is, if I have an instruction breakpoint, do this, and break into the debugger. Is this the only place where I play with breakpoints? I feel like, oh yeah, this is how I take care of watch points, basically data breakpoints. Yeah, I don't know. I know that so far Bedlam has been the one that's caused me the most pain, because it does this really weird thing where they basically looks like they use the interrupt handler to like do their game logic, which is a bit strange. I don't really know why. I don't know what the advantage is to that. Most games don't do that. So all right, so this is where we register on the memory bus callbacks that say every time there's a read or a write, see if there's a read or read-write breakpoint, and then do that thing. So that's not interesting to us. I think what we're going to have to do is something here where we will get breakpoints. Oh yeah, so this gets a breakpoint. Okay, so this is looking at breakpoints on specific addresses. Same thing here. So this is always a concept that breakpoints have to do. These are not non-conditional breakpoints. Okay, so here's what I'm thinking. I'm imagining something like this, right? I'm here and I would have to do some kind of like while auto breakpoint equals to conditionals. I don't know. So we get all the conditional breakpoints. We start to iterate over them. So this, let's say, returns a vector of conditional breakpoints, something like that. And then what we do is we say if, and like the idea here is that there's going to be some kind of stood function, like a function that returns bool and takes no parameters, that tells us, did we hit this conditional breakpoint, right? So something like, what would I call it? Something like this. If condition true, then we remove it. And we break into the debugger. Okay, so this is like basically adding conditional breakpoints. And my idea is we do something like this, and then if we, like, I'll just drop this down here for a sec. We go look at how I handled, let's say, next. So in next here, if the current instruction is call, I should say is a call, add a temporary breakpoint. That's what I had done before. This is what I was explaining, right? So I grab the BC, I say if it's a call, then this is what I was doing. Get the next instruction address and add a once breakpoint on it, and then we resume. But what we want to do instead is something like add conditional. This is not really going to be the interface. I'm just sort of messing around, and we'll fix it after. But it'll be like this, where you put a lambda expression that will return true, and we'll say return what? We take the call stack. Okay, I'm going to need to capture. Okay, call stack frames dot size. So for next, what did we say? We said it needs to be equal to the current size. So when, yeah, the only thing with this is that I won't detect when it's less than or equal to if I do it this way. So maybe what we want is, we want kind of two parts, the condition and then the thing to do when the condition is hit. Yeah. Okay, let's just kind of work this out. So let's say there's like two parts. So this would be the condition. So the condition says if the call stack frames size, and what do I want to compare? I want to compare the CPU registers dot stack. So if the stack is ever less than or equal to, greater than or equal to, because it becomes smaller as we push. This, so this is like the function that tells us that we've hit our condition, right? So this is the condition. And then on condition true, let's say, what we want to do is we're going to want to actually check. So one thing for sure is when it gets hit, it will always be removed. I think, unless we want to make conditionals that, I guess this is a once conditional. So we need to specify if that's the case or not. So yeah. But what I want to say here is if it is greater, that means something went wrong. Like if it's equal, we're good. But if it's greater, that means we're not good. So here it'll be like, I don't know, printf, warning. So I'll say like, anyway, I don't know what to write here, but it'll be something like, stack frame was, or function on stack was exited. What's the word I'm looking for? Unnaturally. Or I can say function did not return normally. Something like that. And ultimately I should like output which function, which stack frame. I can do all that later. You know what I mean? And so we do something like this. And then of course it would be similar for the finish. So yeah, something like this I think would be cool. So let me think how we're gonna do this. Exactly. Let me go look at my breakpoints here. Because the way I design breakpoints, I have this breakpoint class. Instruction read, write. We store the type, we store the address. So there is here an assumption that a breakpoint has to do with an address, which is not going to be true anymore for conditionals. So maybe what I should do instead is actually separate the two, not mix the two. This could be like a instruction breakpoint or an address breakpoint, and the other one could be a conditional breakpoint. And my breakpoints contains vectors of both. Because here we have a map of address to breakpoint. This makes a lot of sense. We don't really want that for conditions. So should the first, maybe. I probably got this wrong. Let me see. So, okay, so every time we push, the S will become smaller, right? So what we want to know is, did it become bigger than or equal to the stack frame? Effectively, the normal case is it became equal to it, right? That's the normal case. The abnormal case is that somehow during the time, so I actually think it is supposed to be greater than or equal to. Because I want to stop, I want this breakpoint, this conditional breakpoint to stop when the CPU's stack has gone back to being, am I right here? What am I doing here? No, sorry, what am I doing? It's not the stack. It's not the value of the stack. It is the, I wanted to use the number. That's right, like what I wrote here. Yeah, okay, so we want to break when it drops back to the current size. Right. I want to capture the current size. Okay, so something like cur stack size equals to this. And we want to stop when, well, I say cur stack size. This is the one I want to remember. This would be like, it's like the stack size at call, So let's just call it that. Stack size at call is equal to this. So when the stack size at call, or I should say, maybe it's easier to go the other way around. When, what did I write here? When it drops back to the current size. So the stack is going to start growing. When the stack size becomes less than or equal to the stack size at call, then we're done. So the stack is growing, it'll shrink back to equal to or less than or equal to the stack size at call. Yeah, that's it. And actually what I'll do is, because I'm gonna need this in both, so I'll capture it in both. Something like this. This will actually have to be on the outside. Yeah, the only reason I need to do this is because capturing by reference, I don't want to capture this guy by reference. I need to capture it by value. Otherwise, I'll be taking the reference of a stack variable, so that would be bad. Alternatively, I could just say capture the, I guess I could say this here. That would be more clear since I'm accessing a member. So I won't accidentally capture something like a local variable by ref. And then here what we're saying is, if actually the, so this inverts, if that current stack thing is smaller than the stack size at call, so this is the current stack size is smaller than the stack size we were at the call, then something went wrong. That makes more sense, right? All right, so let's call this or maybe location breakpoints, you know? Okay. So a conditional breakpoint will be made up of two functions that return, well, one of them will return bool. I'll call this the condition func, and the on condition func. I think I won't call it on condition true because I think it's sort of implied. I actually made that a struct, so maybe I'll just make this a struct as well. Do the good old dance of setting these this way. On. Hey, why isn't my formatter working? Just give me a second. Oh, it's on. That was weird. Don't know why it didn't format before, but there we go. All right, so we have conditions that we store. Is there anything? Oh yeah, we need to know whether it's a once or not. So this is just the kind of fluent interface thing there. So when you create this breakpoint, like here you can create a breakpoint and then you can do .enable .once, for instance. You can say .enabled false if you want, .enabled once equal, once false. Sorry, .once false, and you could just chain them. So I'll do the same thing here because I do need this to be a once type. All right, great. Now in my breakpoints, I'm going to need to store this because I'll use a vector. Although vector might not be the actual best container for this, since I'll, maybe be removing some from the middle. But we'll see. It's fine for now. In fact, I'm going to move this up here. Yeah, so unfortunately now these functions add, remove at index, we sort of have two types of breakpoints, and it's not quite clear what's happening here, but I think that's all right. Yeah, because here I've sort of removed by address, remove at index, and I also have remove all, which, yeah. So array list is a vector, if I'm not, if I remember correctly what is in C#. Right? Because an array list is not really a list. It's just a contiguous block of memory, right? And it'll reallocate when it needs to into another contiguous block and copy. So that's basically what std vector is in C++. It's random access. Yeah. So probably what I'm going to do is I'm going to rename these to like add location. Because Jono, you mainly program in C#, I think, right? That's what you told me. You haven't done much C++. Alternatively, I could. No, it's okay. I was gonna say maybe I should have like another class for, one for location breakpoints and one for conditional breakpoints, and have like two sets. That would be another way to go about this, and then I could sort of keep the same interface and keep this all kind of clean, because I'm not really getting much out of mixing the two, apart from Yeah, actually there's a bit of a problem here because all of this like getting at index and stuff is so that you can list the breakpoints in GDB. For conditionals, I won't really be able to list them here. And in fact, I don't really want to list these ones because these might actually be, you know, so-called hidden breakpoints because they're just sort of internal. But I still feel like it makes sense to use the breakpoint mechanism because really it is exactly what I'll be doing, right? I'll be looking for something, and when I find it, I'll be breaking into the debugger. So it sort of like fits the model. So you started a project in C++ but haven't touched it in ages. I've gone through all the Rust learning modules, but I haven't really found a project for it yet. It sounds like you learned more Rust than I did. I started the Rust book, and I think I got to the chapter on modules, and then I sort of stopped there. Yeah, you know what? I'm gonna undo all this. Change my mind. I'm gonna make a separate class. If ever I want to join them later, I'll do it. But for now, I think it'll be actually easier for me to treat them separately. Because even for display and stuff like that, I got to think a little bit about it. But I think right now, trying to mix the two together will be weird. Yeah, there's just too many assumptions being made about like even how to display breakpoints based on address and stuff like that. So I gotta treat them separately. I don't think it makes sense to mix the two in the same class here. So I'll start with that, and we'll see where it takes us. Now here, I'll just bring these names in because it'll be simpler for this code here. Yeah, All right, I'm gonna go with this. I never know how I should go about this. In this case, I'm gonna just make these helpers at forward. The other way to have done this would have been to have the user create a conditional breakpoint and just add it. That could be another way. It's okay, I'll go with this. So what we want to do here is conditional breakpoints dot and place back, and we just forward. Complicated C++. I was just thinking about how it's going to be difficult to remove this. The project I started was to integrate with the Hyper-V API, essentially creating my own hypervisor similar to that of WSL2, and I've been thinking if I should switch to Rust or stay with C++. What is it that you want to do with this API? What would it what would you do with it? I like to use it as a container for dynamic recompilation for a series of emulators I'd like to develop. I don't think I understand what you mean. You mean you want your emulators to do dynamic recompilation? So are you saying something like your emulator will need to do some dynamic recompilation and you'd like to make use of Hyper-V to be able to access, say, an install of Ubuntu and invoke tool chains like GCC? Is that what you mean? But yeah, yes, but instead of doing it natively, running them in a VM. I do wonder though at that point, why not, you know, interface with Docker instead? Wouldn't that be easier? All right, so let's say I've got this. I'm also, I'm gonna need to do like a remove, but I'll worry about that after. Although I will need it pretty soon. Okay, let's just start with this. And we'll add as we need. Okay, so we've got our conditional breakpoints. So my debugger will have, as we have breakpoints here, I mean, I don't want to discourage you or anything. I just, maybe I just don't understand. I don't fully understand the order of what it is you want to do here. But I mean, it sounds cool. It sounds really interesting. I don't know a lot about, that Hyper-V API. I've not really read about it. I understand the principle of it. I understand the WSL, or at least I know Windows has Hyper-V and that WSL makes use of it. But I do wonder if it's like, is it difficult through the Hyper-V API? Like, are you going to have to do a lot of the work that is already being done? So let's say I had a Nintendo 3DS emulator, Xbox emulator, and a compatibility layer, and TVDM for 64-bit Windows, looking to standardize on an emulation architecture. Okay, sort of understand. I guess the part I'm not quite fully getting here is the need for the VM and where the dynamic recompilation comes in. Is this for, like, when you say dynamic recompilation, are you saying JIT? Okay, so here we're going to add to our conditional breakpoint, or not. Yeah. Oh, I think I put the wrong type here. Oh, right, and I should probably move these. But that does not explain why this is not going to compile. So I need one function for the condition and one for the other one. This is the function that returns true and accepts no arguments. Oh, okay. I do need to put this here. Same here. All right, let's see. Is this good? Does this make it happy? Return, get rid of that. I need a comma in here. There we go. So this is the condition, and this is on condition. Oh, and we also want to say dot once. Cool. Now, of course, I'm going to need to do my check for breakpoints differently now because of this. I'm going to be using conditional breakpoints. Interestingly, I think I could what? Right, so if I'm doing this here, I guess I'm going to have to put the break into debugger here. That's a bit weird. All of this is a bit weird. See, because normally what I would have done is I would not have put this on condition. Okay, so let me read what you wrote here. I guess so for CPUs that are not x86, in order to perform DynaRec, you execute the x86 equivalent for speed. Okay, dynamic recompilation. Rather than running this in the current emulator process, I'd like to run the x86 instructions in a VM. For something like an Xbox, the instructions can run natively. It isn't necessary to run it in a VM, but I kind of like the idea that I get pausing and save states for free. I'm sure it's not as easy, but just teasing out the idea. Also, if I want to allow running 16-bit games on a 64-bit system, running in a VM could be easier, and then thunk Windows calls to their native OS libraries. In this case, a VM can provide containerization. Docker, I'm not sure, would be suitable in these cases. Ah, I see. I see. So, am I understanding correctly that what you're saying is, let's say you're emulating your 16-bit, SNES, which uses a very specific processor. Would you be running a VM that runs that kind of, like, how can I say? You'd want to run a VM for that processor? I guess what I'm missing here is normally what I'm used to seeing, even for a JIT, is in an emulator is something like, we know the native, like for example, say the Vectrex. I don't have JIT, but let's say like it's the 6809 CPU here. I'm effectively translating each instruction one at a time, and I'm executing code that's been compiled for the target platform. But I could, rather than do that, I could, look for patterns or look for functions or hot functions and attempt to JIT them into something that's much more optimal and a slightly higher level. So rather than do it at instruction per instruction level, I take a full function and JIT it into very optimal code for the target platform. That's sort of how I see it, and that still would be in process, and it would use some kind of JIT engine that can target my current processor. That knows both, that knows the source architecture and the target architecture, and can compile from source to target. but I guess I'm perhaps just missing the picture here. But you know, it sounds really cool, and I totally encourage you to try it. And maybe if you do and it works out, like you can show the world, and I'll understand. Or if you write a design document or something like that, maybe you could share that. Be really interested to see. Yeah, so the thing that's bothering me here is the fact that I'm doing this, and the only reason I'm doing this is because of this frame size is greater than or less than, you know. Oops, sorry. What I was thinking now is that maybe what I could do is, like, what if instead of having an on condition like this, okay, because in effect, like, they're practically the same thing, right? All I really care about is something like this. If it's less than that, I could even like print the warning in the condition check. It's a bit weird, but knowing that we do this and we immediately return true. You know what I mean? And otherwise we return that it's equal. So here what we're saying is the condition is that this is the real condition. What we're hoping to see is that it's equal. If it's less than, we print a warning and we return true. We always return true. Like if it's less than, we'll return true. If it's not, it might be equal to, which is good, and we have no warning. And if it's greater than, then we're not done with this condition. And if we do this, what it means is that I can keep my code outside, you know, what to do when it becomes true or not. Like I can remove and all that stuff here, rather than bring the code into the breakpoint and have it execute stuff. I don't know. Yeah, I think I prefer this. Yeah, I'm gonna go with this. So much API design. Okay. And now oh, it doesn't like something. What did I do here? All right. Okay. Good. So the next thing is I need to be able to iterate over these. So the way I did that here is I did that classic get at index and do num. To do that, unless I just return the vector itself, less of a fan of that. But I do like range-based for loops. Oh yeah, what did I do for removing? right? I'm going to have the classic problem of iterating and removing and all that if I do it this way. Okay. All right, if the condition is true, we're going to if once is true, we need to remove it. Yeah, so that's it. I can't do it with a range-based for loop because I need to iterate. So this is what I was worried about. Maybe what I can do is do something like this. All right. If it's once, iter equals. I need the container. Can't win. So close. Okay, and break into debugger. Finally. So just to go over that quickly, we grab all our breakpoints, our conditional breakpoints, and we iterate through them. And if the condition function is true, then it's time for us to break. Now, if it's a once condition breakpoint, we need to erase it. And this is the classic STL safe non-iterator invalidating pattern there. So you call erase and it returns the next, like it returns the iterator that you can plus plus to get to the next one safely. You see, we don't need to do that for for this guy here, because for location breakpoints, we just need to check exactly one location, which is the current program counter. But conditionals, we have to evaluate all of them all the time, and that's why we got to go through them. It's a different beast, really. Actually, one thing here that's not quite right is we might hit more than one breakpoint on in one shot. So what does that mean? Is that like, what do we do in that case, you know? So I suppose what we should do then is just track, like if there really are multiple that return true and we have to hit them all, yeah, let's do something like this. I'm going to wrap this into its own scope just to make it a bit cleaner. Okay, and I should also print, like I'm doing here, you know, ideally, when adding the conditional breakpoint, it would be nice to actually store the condition text itself, but yeah, it's going to be less interesting here. I'll just say conditional breakpoint hits. In fact, I don't really want to print this if it's a invisible one, right? So I don't really have that notion yet. Maybe I'll add it just to conditionals, and we could add it to location breakpoints later. Yeah, you see what I kind of did is I made it so that once breakpoints are inherently quiet, if you will. Yeah, okay, maybe we'll do that. We'll make once breakpoints inherently quiet for now. To do output something useful like the condition text. We don't really have this yet, but if ever I add proper conditional, and I probably will do it, the ability to add proper conditional breakpoints, if I get the string itself. So I'm thinking ahead now to this source level debugger that I'm going to be doing with DAP. You know, we can add that feature, the conditional breakpoint feature, and in that case, I think the condition will be typed in by the user, and I'll get that as a string. And if I can interpret it correctly, I can actually store the string, and we could say, you know, here's the breakpoint that was hit. I don't know if we have to actually output that because it'll just sort of, yeah, I'm not sure yet. I have to look at the protocol. Maybe it takes care of it for me. But anyway, for now, I don't really have this problem, so. The other thing I should be doing is like displaying conditional breakpoints when you hit info break, which I haven't done yet, and I don't think that I'm going to do it now, but it would be in here when you do info break. I'll just stick a little to do in here. Display conditional breakpoints. And here I'll also say to do don't display once breakpoints or add a hidden property. Something like that. So much to do. All right, so now we have a way to add them, to break, and to remove them. Okay. So technically speaking, next should work as expected. If I hit next, next, next. What I haven't done yet is the part that does call stack removal, right? Based on the stack pointer. So yeah, I should totally do that part. Where was that again? Here. I'm just sort of debating in my head whether I want to sort of only look at the stack pointer or whether I want a mix of both. Because sort of the mix of both is like, you know, this is the normal, and then I can detect these sort of abnormal. And they're both valid, but I would have a way to say put a breakpoint, or I could print when it's an abnormal, you know what I mean? Which is not really a terrible idea. Sorry, just trying to figure out what's the right move here. Okay. And I was saying that I need to do this in a loop. Right, so what do I do here? What do I do? So we grab the stack. I'm just looking at this code here. I basically want to run this, but I want to keep doing it and popping until this condition is no longer true. All right, so something like while, and I think I can actually do this now, right? While, initialize that, and this is the case. This is a C++ 17 feature right here, if I'm actually correct. Was it just for if? Oh, it's for if. We need this in while. Actually, you know what I'm going to do is I'm going to add a function. Yeah. And I'll just say un16 t top, last stack pointer. If I actually have frames, but anyway. I mean, I shouldn't really worry because we'll always have one frame on there. But anyway. Okay, so what I'll do instead then is I'll just assert. I'm not using this keyboard yet. Back dot stack pointer. Yeah, I still want to assign it to something though. Do I prefer my new keyboard? So yes and no. I actually prefer the old keyboard for many things. I like the build, the curves, the weight, the size. All of that stuff is better on my Matias Ergo Pro. This one here is from Kinesis, which is actually a really good company. They make great keyboards, but I find the build flimsy, thin, kind of light, lighter than I would have expected. I'm not a huge fan of the layout of the keys. I kind of prefer them on the other keyboard, just the way they cluster keys and stuff. It's a bit bigger and wider. The one thing about this keyboard that I do love though are the switches. These are Cherry MX Browns. You can choose which kind of Cherry switches you want. Unfortunately with the Matias keyboard, you don't really have much choice. They have their own kind of custom key switches. There's these like Matias, they're sort of based on the old Apple switches, but it's their own thing. And so you can't put your own switches. You can't have Cherry switches on it. So yeah, I prefer these switches, but I prefer pretty much everything else about the other keyboard. So if Matias could make the Ergo Pro with Cherry switches, I'd be like super happy. But you know, it's not this. And when I'm saying this, I'm not saying like this is a terrible keyboard. You know, say the Matthias is like a 9, this is an 8, something like that. You know what I mean? That's the thing. You see, I really, really wish that I could do that thing I can do with if statements. You know, you can do this with if statements. You can say auto, you know, top stack is equal to last stack pointer, and then you can actually put a condition here. You know, top s is greater than 0, and exactly what I have here. This you can do. But you can't do this with, you know, why can't I do this with a while loop? That would be cool, right? Every time you start the while, do this, and then do this condition. And I could do it with a for loop, but then I would have to repeat this, you know, like this. Do this initially and then repeat the assignment. It's kind of crappy, you know? I have a ducky with cherry blue switches. It's weird. It's wired, but I think next time I'll go wireless. This one's wired as well. Duckies are nice. I considered getting one. I haven't tried blue switches like for a long time. I've tried them, but I haven't like tried typing for a long time on one of them. They're pretty loud, right? Like, do you use those at work? Do people complain if you do? Okay, here's what we're gonna do. Is stack pointer what? Stack pointer. Is frame stack pointer. I don't know what to call this. I need to be able to describe this. Is return address off stack. Like I'm rewriting what I wrote here, you know? Now I can do At home, they are loud. Yeah. Yeah, the MX Browns are at least are quiet enough. Interestingly, though, they're a little bit louder on this keyboard than on a normal keyboard because my keyboard is raised. You know, it has like these, you can see it on the camera there. It's got these like legs here. In fact, you can raise them really, really high. I don't go as high as the max height, but because of that, like they sort of have like a bounce. Like, because I suppose there, you know, when a keyboard is flat on your desk and you're typing, the desk is absorbing a lot of the shock. But when they're elevated like this, there's kind of like a lot of air and there's a lot less absorption that occurs. And so you sort of hear the ringing out or perhaps the vibration of the plastic. It's kind of interesting. Okay, so I think this might make it a bit more clear. So I think finally we can see if this actually builds and maybe test it. It does, of course, does not build. All right, so let's take a look. What's going on here? Missing functional. You know that thing where you hack for a long time and then you build and it actually builds right away and you're like, what? But or even better, when you hacked for a really long time and not only does it build, or maybe it doesn't build, but then you run it and all this code you wrote actually works the first time. You know, that mythical thing that happens like twice in your life? It actually just happened to me at work a couple days ago. Or like yesterday. I was like working on this thing and like I think I worked on it for like an hour. Changed so much code, refactoring things and adding new logic. And like it didn't build right away. I had to like fix a couple of build issues. But I was like certain it wouldn't work. And then I ran it and all the unit tests passed. And I was like, what? No, can't be. Start putting breakpoints everywhere. Then I'm hitting the breakpoints I expected. Then I'm like, okay, try and break it. And then it breaks. And I'm like, holy crap, it actually worked on that the first shot. And that really rarely happens. Like you code so much and then it actually works. Anyway. So that's like. No, things are going really well at Google. Actually, it's really, really interesting. And what's really cool is that everything I work on is open source. It's I work on Chrome effectively on the GPU team for Chrome, and Chrome is developed in open source, and the project I work on, which is called Swift Shader, is open source as well. So what's funny is that you could actually find out what I'm doing day by day by just kind of looking me up. You'll see my changes. We have a mirror of Swift Shader in GitHub, but the original source is in like googlesource.com, I think it is. So it's like their own open source repo thing. But yeah, anyway, so it's really interesting. Learning a lot. Great people. It's a good company. I really can't complain. Yeah, okay. Thanks, Jono. It's nice of you. And how are things going for you at your company? Are you still at the same place? Okay, so this is building. So let's actually see what happens when we run it. I suppose I should put some breakpoints here. Just give me a sec. Yeah, let me just stop this for a second. I'll go put one on my next code here because this is new code. So I want to see what happens when we do a next like that. And I want to see when conditional breakpoints are actually being looked at here. gotta remove this. Let me do that now because I always forget. All right, so there's that remove from stack that we expected, right? Is return address removed from stack. So it's the abnormal return. So we're gonna pop our guy from the call stack. Remove this hexadecimal display at F10. And then there's nothing weird anymore. Cool. So now and we're good here. Cool, that actually worked. So now what I want to see is whether next will work. So let's go all the way until we get to a instruction that has a jump. I have no idea when that's going to happen, but actually, let me just do next. In fact, I can just kind of do next until I hit a breakpoint, right? Because I have a breakpoint on when a next happens and it's a call. There we go. So there's our breakpoint. So we're obviously executing a call. I wish I could. Oh, there we go. So we're doing a jump subroutine to clear XB. This is a BIOS routine. So in here we detected that it's a call. We're going to get the stack size at the call. So right now the stack size is 1. And we're going to add a conditional breakpoint here that says break when, as we said. So actually I'll stick some breakpoints in here. Unfortunately, I can't put one there. And really we should not hit this one here. But this one we will eventually hit. So let's just move forward. F5. Looks like I did something bad. What did I do? Access violation, writing location 040. That must be this once call. It's during the in place back. Oh, is it because we're... What's happening here? Call add. Okay, so let me just check something because cmake lists here. Cmake lists, no. Cmake lists.text. I want the one for the debugger. Okay, so it isn't optimized. So why is it that I couldn't see this here? So my suspicion is that add here. Oh, did I return? Oh, funny that MSVC does not complain. I said that this function returns a conditional breakpoint by reference, and I returned nothing, and it didn't even complain. No warning, nothing. And I have like all warnings enabled and everything. Like MSVC, man, sometimes can be really strange. What's your problem? What's your problem? Oh, no, it's not actually this that I want to return. It's the breakpoint itself. In place back. Decal type auto. Does it? I think this returns the thing. It's going well. I think last time we spoke I was between jobs. Picked up a new role and yeah, doing well. The people are very nice and the culture is good. That is great to hear, man. Oh, I broke this. You know what they say, right? You stay for, was it leave for your boss, stay for the people? The emphasis being on the people right there. So important to work with people you like. Like this. Next. So let's run until we hit our breakpoint. It's gonna lift this up a bit. Whoops. Too many enters. So there's a jump. So we're about to do a next. Hopefully this one will work. So we actually do the add. Perfect. And resume from debugger. Now we are going to evaluate conditional breakpoints. Oh, that was slow. Great. So there's no more. I'm going to do it again. That is slow. Okay. And then we're going to put a breakpoint inside. So eventually, okay, there we go. It just returned true. And we're going to erase it. Wait, why did we just iterate again? That's weird. I'm gonna crash here. My erase should have done the right thing here. We're iterating forward through conditionals. When we erase our iterator, we get the next iterator that we're supposed to plus plus. Oh no, we're not supposed to plus plus. That's the thing. Jono, don't do C++. C++ bad. You see? Look how ugly this is. I'm sure, I don't remember how it works in C#, but I'm certain it's easier. I think you have like an enumerator or something like that. And yeah, I think that's what it is, right? You have like an enumerator and you can just say like remove the current value and then everything just kind of works because it's the whole enumerator model just is easier to work with than this iterator model. Well, if you're for eaching and you need to remove something in the middle of your what's it called? Array list. You know, does that not invalidate the for each? Because that's the problem that we have in C++, right? You have this iterator, which is effectively a pointer. And then you're saying, here, remove this thing in the middle. But now your pointer is pointing at something that has been removed. And then you plus plus, and you'll probably skip the next item. That's the problem. And the solution in the standard is to call erase and have it return to you the next iterator. You know what I mean? Oh, wow. Looks like, yeah, we were right. I happened to break on a jump call, so beautiful. So let's do this. What's happening? We are probably stuck in an infinite loop. Or something. Yep. Are we? What are we doing here? Yes, we are. We're stuck in an infinite loop. Why are we stuck in an infinite loop? Oh, right. Gross. Yeah, Link is so cool. So, you know, I did quite a bit of C#. Before I joined Google, I spent quite a bit of time working on Git extensions. This thing here. In fact, I added the submodules thing you see here in the pane, in the left panel. So this wasn't there. And you know, I did some work and I fixed some bugs, and ultimately I wanted to get this feature in, and the team invited me to join them, to actually become a part of their team, which was great. And you know, I fixed a whole bunch of other stuff while working on them. It was really, really cool. But then I started working at Google, and you know, just didn't have the time anymore, so I put that aside. But this is all in C#, and it's in like fairly modern C#. They're using async everywhere, link everywhere. So I had to like basically brush up on my C#, learn async, because I didn't know anything about async. So yeah, that was pretty interesting. Oh, have you been contributing to it? That's super cool. I'm sure they appreciate it. They're a good bunch, really a good group. A lot of them work at Microsoft, actually. Which I guess is no surprise. It's a successful project, and it's written in C#, so probably, you know, good C# programmers. I mean, not probably, actually. They are really good. Yes, the new updater functionality and working on fixing the installer. So you did that? I like the new updater functionality. Like the fact that it actually works. The fact that it actually does an in-place install. Is that what you're talking about? So, okay. So basically, the problem here is I would have to do this. You see how much grosser this just got? I'll just put it in for now, just so that we see. So you made it possible for Git extensions to update itself. Because before you said like say, oh, there's a new version, and then you download it, and then you'd have to like install it yourself. So you're talking about the whole fact that it downloads and just runs the installer. That's what you did? Okay, so here we go. Erase should break, and we break. Perfect. Yeah, yes, it took you to the website originally, and I implemented code for GE to download the MSI and run the upgrade. Nice. I totally noticed this. Like I recently updated, right? And I think there was another update, and then it's like, oh, it just installed the update. That's awesome. That's really great, man. Very happy. Very happy to hear that they're getting good support from people like you. All right, so here we have a jump that we did, and we ostensibly returned from it here. And in fact, if you look at the addresses, it does make sense. See, we were at 09E0. This is a 3-byte instruction, so we're now at 09E3. And if I look at the trace, just 10 lines of trace, see, this is where it gets confusing when you look at the trace, because I really, really gotta do this better. But anyway. So ignoring the LDD here, we can see that we were in the middle of these, like we were in this F range. So we were executing this print string, and then we got back from it. So this looks like our next is working. So let me just disable some breakpoints here. Hey, every feature is important, man. Like, and you know, you start small, and you know, you work your way up. like I had this, you know, vision of like adding the submodule thing, and it took me so long to finally get that in. I actually had like a proof of concept in, like, you know how it is, right? I had a proof of concept of that submodule thing. It took me like, I don't know, 3 days. And I think it took me something like 4 months before I finally got it into the thing, because, you know, to get it there were like minor things that weren't quite working great. And so I sort of started working on those and fixing problems that were all sort of related, but not indirectly related. And then as I fixed those, I fixed more things, and eventually finally made my way back to that feature, cleaned it all up, and got that in. So, you know, it's just funny how that goes. But yeah, every feature is important. So I wanted to put this here again. Okay. So I'm going to do some more next. There's another one here. Just want to kind of keep it moving here. So here's a clear. So we're going to do next. Looks like it worked. See, what's cool is that when you run next, you sort of stay at the same stack frame, right? Like I'm in the middle of the start right now. So if I just keep doing next, I'm basically staying there, especially because start never returns, right? So you get see, now I'm running a whole bunch of what is this, CWAI, and now all of a sudden it's waiting for an interrupt to occur. So this is just going to take a really long time. See, after that instruction, I will eventually hit this one. CWAI being super weird, but if I like put a breakpoint on this, there we go. So we hit our interrupt, and now I can start doing next again, or not. Ah, right. It gets confused. Yeah, CWAI messes everything up. So actually, if I put a breakpoint instead on 0, 0, and what would come after this? I guess 0, 1, 0, 1. There we go. So this means that we finally got an interrupt. Return from interrupt. So this looks like it's working. Oh, back into CWAI. So the next thing would be to do the finish, which will be very, very similar. So it's right below here, finish. So if we base ourselves on the same idea, what we want to do is, well, I'll just copy this. This part here. Oops. See, keep messing up on my keyboard there. So for finish, what we're looking for is, what is it that I wrote in my notes? We break when the call stack size will be the current size minus 1 exactly. So yeah, so I kind of like this name. So we say stack size at call, right? When it's equal to the stack size at call minus 1, it means we're good. If it's less than the stack size minus 1, it means function did not return normally. Exactly the same idea. You can see they're very much the same. All that changes is which target which frame size we're expecting. So this should make finish work. So let's see if that's the case. Okay, let's get into the game. All right, so if we do a backtrace, we're in the middle of print string yx. So if I do finish, I should now have gone out of that function. So sure enough, I have. And I think we can see here, we were at F4B8 in F378. And we had left off at 09E0 when we went into there. So that means that we should be at just a couple of bytes ahead of that. So it looks like we were 3 bytes ahead at 09E3. So that makes sense. If we just continue a bit, try and get a more interesting backtrace. We're sort of in a print string right now. I don't know if print string will call something else. Doesn't look. Oh, what's this? No, these are just some tests. Yeah, this is not the most interesting of functions. Let's finish that one. Dot here, dot dwell. What's our backtrace there? Okay, we're in dot here right now. Still not super interesting. Jump subroutine. Okay, what's our backtrace? Okay, so you see we're too deep right now. We're doing rotate VL AB, and then that called DP to C8. If we finish, we should now be only 2 in, and if we finish again, we should now just be at somewhere in start. 04 AD in start. Ah, here we go. A nice big stack trace. We're like 5 deep in here. So we're in the process of doing move to D7. That's a BIOS routine. So we could try finishing this one. And we've got ourselves up here. 740. Now we're at 743. 745. No, now we're inside another function. Great. Finish, finish, 736, finish again, 778, next, finish, and we're back in the start. So there you go, success. You know, I probably should write a proper thing to test this. Like, I wonder if I could write something recursive in my game and actually see that this works with the recursion. That would be interesting, wouldn't it? But I don't even know if if the compiler will do what we expect for that. This compiler can be kind of strange. So like here's main. So let's try like a recurse function, and what we'll do is we'll just give it a count, and we'll what do we do? We'll do like a printf, so at least we have something to compile in there. We'll say count is %d count. And then we'll say return recurse of count -1. And then we'll need our if count is equal to 0 or -1, let's say, return. No idea if this is going to work, but let's give it a whirl. So let's start at 5. Whoops. So this is build. It built. That's a good sign. Let's see if it runs. I'll just try and running it. This will actually launch another Vectrexy here. Looks like it worked. 543210. So we know that it works. Now what I would like to do is actually debug it. So how will I do this? I need a break at main, basically. I don't really have that. Okay, let me see if I can get the symbol for main, get the address for it. Here it is, 0AD2. So what we'll do is we'll come in here and we'll put a breakpoint in my startup script on 0AD2. And we'll start it, I'll actually do it from here. All right, so breakpoint hit at 0AD2. If I just do a little trace, so we can see that we just jumped into main. So that's cool, right? And we just do a little bit of stepping. What we should see is there's recurse. Again, these names are mangled for C++. You can see here that, you know, recurse takes an integer, which is why it's called recurse I. I don't remember what the Z7 stands for, but it's probably related to the calling convention. So we're going to step into recurse. We're going to do some load, store, compare, branch if equal. So we're looking to see if we're at the 0 case. We're not. I think some of this is the printf stuff. Now we're going to, yeah, this is jump to 0f01, push y. I think this is going to do the printf. Debugging. How come I'm not seeing the print here? Oh, there it is. Oh yeah, sorry. Most of this code was just getting, like, pushing a value, pushing the count to Vectrexy, and then this one here caused it to print. In fact, it's this one here that caused it to print, but it prints before it outputs in the debugger. So that's cool. And now we're going to recurse. So we should see a recursion. There we go. So here's the jump subroutine. So just to show you the backtrace before we recurse, we're in start main recurse I. Now we're going to step inside that routine, and we should see 2 recurses on our call stack. Right? That's cool, right? So let's put a breakpoint here so we go a little bit faster on this line. So we're going to step into this one, and I hit a breakpoint. Yeah, interesting. Why is it saying breakpoint hit at 0AB2? I didn't add that breakpoint. Oh, this must be related to, I have no idea, actually. So I must have messed something up in my breakpoint code there, because that's odd. That's odd. And we hit this here. So maybe, see, I was going to enable this assert, but maybe I can't. Oh, that's interesting. So maybe what this is going to show me is that when it comes to recursion, oh, that was a call. Okay, 5. So we're back here now. If I look at my backtrace, we have 3 recurses. So what? 2 question marks. Like, first of all, what is this? Hey, what's this? Added breakpoint. Did I do this? Oh, here it is. Oh, I did add this breakpoint. I'm such an idiot. Okay. Sorry, I added this breakpoint myself. This is the breakpoint for the jump. I just got confused because Visual Studio broke at the same time that I hit my breakpoint on the same frame, which is pretty weird. Yeah, so it makes sense. I mean, if we're recursing, of course we're going to see at one point that we have the program counter is going to be equal to that on the top of the call stack. So that's okay. So this is not something that I need to assert. It's fine. So I need to delete this code. That's what it means. Okay, so if we continue, so we did count 4. We're going to do count 3 now, and we're going to step inside again. Again, we're going to hit that thing, which is fine. There you go, bunch of recurses. And so the interesting bit now is that if I do, what we want to see is that I would be able to do, first of all, finish and only step out of one of these. And since I'm using call stack size, that should work just fine. And also if I do finish now, there is a question about, we know there's still more recursion to do. So will it actually do the output for 4 and 5 and then stop? Sorry, 5, 4, 3. Yeah, will it do, I guess, 2 and 1? So let's see. Let me just take this off here. So I'll do finish. Okay, so it output to 2. I think that's correct. Oh no, because I have a breakpoint. Disable. I should have disabled it before. Damn it. Okay, I did finish and it did. See, it would have done 2, 1, 0. Exactly. It's because of that breakpoint. See, we were here. We had 4 on the stack. I did a finish. If I had not hit that breakpoint, it would have finished 2, 1, 0. So the 3 that are deeper would have just run, and then we would have gone to the parent stack, which is exactly what we expect with this command. Cool. If I do finish again, finish again, and finish again, and there we are. We're in here. So let me try resetting. Oh, so reset doesn't hit my breakpoint. Oh, because I deleted my breakpoints. That's why. Yeah. So it happens when you delete breakpoints. Okay, one more thing I want to try. Because I just did finish. I want to try next. Okay. So what was that? I should have noted it down. So let's just do step. So there's recurse. So oh yeah, that's the one. 0 A B 2. Okay. So we look at the backtrace. We did 2 recursions here, right? We're about to do a third one. If next works correctly, what should happen is that it should output 3, 2, 1, 0, and then we should be immediately after this recurse. So we should still only have 2 left on the stack. So let's see. Huh. Oh, again with the breakpoint. Damn it. Screwing up all my tests. Okay, so let's do this again. We have 3 on the call stack. We're about to execute this. So now we should see 2, 1, 0 when I do next. And then there should still be 3 on the call stack. And there we go. 2, 1, 0. And those same 3 are on the call stack. So that's exactly what I expected. So yeah, if we just continue, let me just re-enable my breakpoints here. Continue, reset, skip. All right, so you're back at the beginning. Hit this breakpoint, and let's go continue, continue, backtrace. Let's do one more continue, backtrace. So now I'm going to do a next. We should see 1, 0. Keep making the same mistake, but it's all right. And there we go. Finish, 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 finish. Disable this breakpoints. Finish, finish, finish. Finish, finish, finish. And there we go. Ladies and gentlemen, this is working as expected. I am quite pleased. I think we have a working call stack tracker. And it should do the right thing with respect to, you know, one thing I haven't really tested out is, thanks, Jono. I haven't tested out like that weird case, right? And you know what? We could totally do that weird, like the case of I had a breakpoint and that breakpoint will not be respected. Not the breakpoint, but like if I want to do like a next, and then all of a sudden my call stack gets messed because, you know, Bedlam is being weird. We could actually see that happen, and we should exercise that. So if we look here again, where was it? It would be here on this address. That's where the funky pull stack occurs, right? So in fact, no, what we want is we want to go on the jump subroutine, which I apparently didn't paste here. Oh no. Yeah, I don't have it. Okay, let's do this. Go back to Bedlam. There's one weird case right there. Okay, so if we go to here and break, where are we? Trace the last 50. Okay, that's the pull stack we were talking about. I wanted to see the jump subroutine that got us into here. So that was, where is my JSR? Here it is. Okay, so it is 0229. So break. Delete star and break on 0229. What's happening? Am I like, did I hit a breakpoint or something? Oh, breakpoint hit. Okay. So here we are. So here's the question. If I do next now, this function does not return normally, right? So let's see what happens. Yeah, I don't know what just happened. Oh yeah, it doesn't always fail. That's going to be difficult. Okay, I know what we can do. Next will be more difficult to test, but finish would be easier to test. So if we go to here, okay, yeah, back on this breakpoint here. Okay, so here's the pull stack. So if I say finish, because right now, right, we have this is the stack frame we're in, and this one will not be cleanly popped into the PC. So if I try to do a finish, we should see, if I'm right, and they did this right, that we should get a warning. And instead I get a breakpoint hit. Why? Why do I get a breakpoint hit? I mean, I know I have a breakpoint there, but this is not right. It's like it's not doing anything. See, if I step, then this happens. But when I try to do finish, it doesn't work. Why? It's a good thing I'm testing this, because see, it's not working. So what's happening? Let's go to finish. Does the breakpoint need to be set to once for that case? It is actually set to once. So here's the finish code, right? So what I'm saying is we expect to be finished when the frame size goes to 1. I guess actually I won't detect it here, right? Because what's going to happen is it will go to 1. But okay, what's going to happen is it's going to be that other breakpoint that will have detected the abnormal case, this one here. All right, but it doesn't explain why my finish. So okay, so we won't see this print here, but it does not explain why we don't actually step out correctly. Because once the stack size becomes 1, we're done with this instruction, right? Hey, look at that. I have a lot of conditional breakpoints. That's not normal either. This might be part of my problem. Oh, I think this is every time I ran fin, it added a conditional that never ended. Okay, so there's a bug here. There's a bug here to investigate. My stack size at call is 2, which is correct. We're gonna be looking for it turned to 1. It will turn to 1. I'll put a breakpoint here, F5. So here we are, starting to look at conditional breakpoints. The condition function isn't true. That's expected now. So it's that it doesn't step it. Let me go see my finish code here. I did do resume from debugger. Something is making me break into the debugger. Let me see what. Put a little data breakpoint on this guy. Oh, here we go. Check for breakpoints. So this looks like it's failing because I have a breakpoint that I put on that instruction. But what does that mean? Does this mean that if I have a breakpoint on an instruction and I try to finish it, it cannot finish? It's possible. This reminds me of something. Where was it again? I had, is it until? I had this like step, perform a regular step. I think it's this. Oh no, that's just next, never mind. I had something where I had to execute, oh here, for continue, that's it. First step current instruction. Otherwise, if we have a breakpoint on it, it will end up breaking immediately on it again. This is it. Okay. I have this problem in a lot of places where I need to resume the debugger. I think this is actually a general problem. Every time I resume from debugger, if I already have a breakpoint on the current instruction, I will immediately break and not actually resume. So maybe I need to fold that into the resume from debugger. Okay, that's something else. It's not for today. Let me just mark that down. Like for continue, where we first step before resuming debugger. We do this. We need to do this for other instructions that resume, like next, finish, etc. Maybe we should fold this into the resume. From debugger function. All right, so anyway, if we get back to what I was working on here, is all I got to do then is just delete that breakpoint, because that's what's messing us up right now. So let's just disable that. All right, so finish. All right. Nope, F5. Yep, I got to take that out. So there's our remove from stack. There's our conditional, and it just erases it, and everything is normal. Actually, it's removing a bunch of them because they accumulated. Nice to know I clean up everything here. All right, so we don't get any warning, like I said, because I'm not emitting any warnings when we detect weird call stack popping. So I do have a place where I could do that, and I maybe should do it, which would be here. You know, print that we removed, print that this was abnormal removal, abnormal stack pop. So, but the good news is that we actually are at the instruction. If we look at our trace, we can see that what got us here was this instruction right there. That's the last instruction that executed. So like I did a finish on this instruction and it brought us to just after it because that's the instruction that you know, did the thing. Like if instead we put, say, a breakpoint on 0682 here, this might just make it a bit more obvious. Okay, so now I'm going to do finish. And still getting that because I need to delete this breakpoint. And then do finish. And there we go. So we were at 682, and now we're at 68C. And if we look at the trace, there's 682, exactly 10 instructions above. And we were running, and then we got this pull stack X, which is the weird bad behavior way of exiting our function, and we stop exactly here. So finish is working. Yeah, so we're not going to get the warning thing because, and you know what? Now I'm starting to think like that there's almost no use. If I start emitting that we're getting abnormal stack pops here, I think then with this loop, I think then there's like really no point in outputting it in our condition. You know what I mean? Like this here. I don't know. I gotta think a little bit about it. Does it make sense to output this here if we're outputting the for outputting abnormal return in updates call stack. I don't know. I would need to repro it. The thing is that this code doesn't do it. I would need to like somehow, I guess I'd have to write the assembly code myself. I could do it. I could write a little routine in assembly code and actually link it into my C++ func code. Like go three deep and then just do like a pull stack, like I said, you know, ABXY, and just pull off three of those return addresses and see what happens. Is it worth it? Not sure. Okay, well, it is getting late here. I'm very pleased that this is working. I think this is a better way to do call stack tracking. And with this working, we should be able now to, excuse me, to move forward and start looking at the DAP stuff. Notwithstanding some of these debugger things that I might have to do. But yeah, I think we're in a pretty good shape now. All right, so thanks guys for watching, and I should be back next Tuesday. I'm trying for Tuesdays and Thursday nights. So yeah, if you want to check me out, I'll see you guys next time. All right, take care.